Hi,
Okay.
I'm Ranjini Mondol.
Hi, I'm Abhijeet Singh.
Hi, I'm Souradeep. In this video, we'll be talking about our recent work, Dark Secrets of Baryons, illuminating dark matter baryon interactions with JWST. This work has been done in collaboration with Professor Ranjan Laha. To begin with, let us recall that dark matter is an integral component of our universe. However, we can perceive dark matter only via its gravitational effect on ordinary matter. But an interesting question to ask would be, is there a secret language by which dark matter talks to ordinary particles? That is there an interaction outside of gravity between dark matter and particles of the standard model? Over the last few decades, researchers have been trying to probe or detect interactions between dark matter and standard model particles, or for dark matter with itself via different terrestrial experiments and astrophysical observations. In this work, we are specifically interested in the scattering of dark matter particles with standard model particles. In our work, we look at the interactions of dark matter with baryons, that is, protons and electrons, in a cosmological context. An important quantity of interest in this context is the cross-section of interaction between dark matter and baryons. For a broad class of particle physics models, this cross-section often has a power law dependence on the relative velocity of the incoming particles. Although this power law index could be various, we are interested in this work at three different velocity dependencies, that is v to the power 0, v to the power minus 2, and v to the power minus 4, corresponding to contact interactions, electric dipole-like interactions, and Coulomb-like interactions, respectively.
So you could have these interactions between dark matter particles and baryons, but how do you go about detecting them? This is where the James Webb Space Telescope helps us. It turns out that if these types of interactions exist, then galaxies of a certain size are formed in less abundance as compared to the case when these interactions don't exist. This underabundance is quantified by a quantity called the transfer function. In this slide, on the left image, we plot the square of the transfer function as a function of the inverse size. The thing to take away from this plot is that the more downwards these three curves come, which correspond to the three different types of interactions discussed before, the more is the underabundance of galaxies of a certain size. On the right hand image in this slide, we show the UV luminosity function as a function of the brightness of galaxies. UV luminosity function is just a measure of the typical number density of galaxies with a given brightness. The yellow dashed curve shows how the UV luminosity function looks like for the case when there are no interactions between dark matter and electrons or protons. However, if you introduce interactions, the UV luminosity functions start to go to lower and lower values as seen in this image. We also note that the UV luminosity function plotted for the case of no interactions is consistent with the data, but the functions for the cases when there is interaction are not consistent with the data, and hence these interactions can be ruled out. But how is JWST helping us so much? It turns out that James Webb Space Telescope is sensitive to the infrared radiation of the electromagnetic spectrum. And to that spectrum, Hubble telescope was simply not sensitive. And if you are sensitive to the infrared rays, only then you can observe galaxies which are very, very far away. And that helps us probe the interactions much better. We are also very proud of the fact that we were able to incorporate the astrophysics informed by the Thyssen Zoom suite of simulations. These simulations have given us an astrophysical model which is suitable to be used at those high redshifts, that is, galaxies which were formed very, very early in the universe. As far as we know, this is the first dark matter interaction study that has incorporated astrophysics informed by these simulations.
So now we have looked into how dark matter baryon interaction affects the structure formation as well as the UV luminosity function probed by JWST data. Let us look into our results. So in this slide, we show some of our results on 95% confidence level upper limits on the interaction strength between dark matter and baryons for different models. So in these plots, along x-axis, the dark matter mass is plotted, and along y-axis, the interaction strength for various models are plotted. So these green shaded regions show our limits from JWST SpecZ data. And the takeaway message from all these plots is JWST can give competitive constraints with other cosmological observations within an order of magnitude, even only with about 40 spectroscopically confirmed galaxies. And remarkably, we find that for one of our cases where the dark matter is interacting with the proton with 1 by v squared dependence, we find that our limits are the strongest, which is shown by the green shaded region in this plot, and these two with limited number of data, and we expect that as more and more data comes and JWST observes more galaxies, all our constraints would get strengthened. So we conclude this work with the essence that why is this exciting to the astroparticle, particle, and the nuclear physics community, as well as a broader physics community, that we put the first constraints on dark matter baryon scattering cross-section with the JWST UVLF data on high redshift galaxies. Also, we use state-of-the-art astrophysics, and using that, we put strongest constraint for broad subset of possible non-gravitational interactions between dark matter and baryons. And as more and more data comes, JWST can provide unique insights into the different beyond the standard model physics scenarios that we are currently trying to probe through terrestrial and astrophysical observations. Thank you.